Hello, everyone. We are finishing chapter 9 this week, starting with 9.4. So we have 3 sections this week. They're all relatively short, though, so hopefully these videos will be short as well. So in 9.4, we are looking at effusion and diffusion of gases, and we're going to define and explain effusion and diffusion and state Graham's law and use it to compute relevant gas properties. So let's start by talking about diffusion. So at room temperature, a gaseous molecule is going to go through billions of collisions every second. And the average distance that it can travel between collisions is called the mean free path. As we decrease pressure, this mean free path is going to increase because now it's not being condensed as much. So it's also, the mean free path itself is hundreds of times larger than the diameter of the molecule itself. There's a lot more empty space in a container than there is size of molecules. So for diffusion, what happens is these molecules are dispersing quickly in a container, and they're moving randomly. In a closed environment, they're ultimately going to diffuse into to where there's equal concentrations of gases throughout the container. They'll still be moving, but they'll keep the same rate of transfer. So one way of looking at diffusion is, let's say you're in a car with your buddies. Come on, pen. Okay. So you're in a car with your friends. And let's say they don't know it, but you had, there's your steering wheel, you had some beans for dinner. And what do beans make us do? They make us pass gas. So you pass some gas. Let's get a different pen color going on here. And anyone who's right by you is going to smell that gas pretty intently, right? And your buddy that's sitting right next to you is like, dude, WTF. And eventually, though, that gas is going to diffuse in the car. And now your friend on the back seat gets to smell it too. Until eventually there's equal amounts of it throughout the car, and hopefully the smell starts going away because the gas molecules themselves have spread out further. So here is looking at mixing two gases. So we've got these two containers. One has hydrogen gas, the other has oxygen. And in part A, they start off separated. And then the stopcock there that separates them is opened. So now these gases are going to start mixing. They're going to start moving around. And in that movement, they'll be able to go through that opening. And they're going to keep doing this. And eventually what's going to happen is they become equally distributed on both sides of the vessel. So a homogeneous mixture. So talking a little bit more with diffusion, we can get a rate of diffusion, and this is the amount of gas passing through a specific area per unit of time. So, you know, if I've got some box of a gas and I want to know the rate of diffusion, I go, okay, I'm going to look at this area here, and we're going to see how much gas is going through this area for however much time that I'm looking at. This is dependent on the concentration gradient. So you might have areas where there's more gas, so it might have a different rate of diffusion than somewhere else until everything is equally distributed. The surface area that's available also changes your rate, and the distance that the particles have to travel also affects your rate of diffusion. Now, effusion, so now with an E, is when gas molecules escape through a tiny hole. So, for instance, balloons. If you have a balloon filled up with helium, a latex balloon, well, all balloons, but latex especially, you see this, after a few hours, it starts getting smaller and eventually gets to a point where there's not enough helium to make it float. It's because the gas is effusing through the latex. The latex isn't necessarily all solid. There's really tiny holes in it, so it's able to escape through it. So it's not the same as diffusion. But both diffusion and effusion depend on the molar mass of the gas. That's going to influence how fast they're moving and how big they are. So they can have unequal rates, but the ratio of the rates are the same. And then we have Graham's law of effusion. And this states that the rate of effusion of a gas is inversely proportional to the square root of the mass of its particles. Okay, so inverse means that the rate is proportional to 1 over the square root of m being molar mass. Okay, so we look at this in terms of molar mass. So if I have two gases at the same temperature and pressure, the ratio of their rates is equal to the square root of the molar mass of B divided by the square root of the molar mass of A. Okay, so notice it's B over A on the square root side, but A over B on the rate side. And that's because if we do 1 over the square root molecular mass of A divided by 1 over the square root of the molecular mass of B, dividing fractions, so this becomes 1 over square root of MA times, we flip the other fraction, so that becomes square root of MB over 1. And so that gives us square root of MB over square root of MA. So just to show you why. But it also shows you the inverse proportionality as well. So this is a nice picture kind of just showing you diffusion versus effusion. Effusion, they're going through this little tiny hole in the center. So this opening is smaller than the mean free path of the particles. Okay, so basically what we're saying is only one particle is able to pass through at a time with effusion. And then diffusion is just the gases jumping around until they're equal in concentration and they're just moving around doing their thing. So here we see two balloons at same temperature and pressure. They're in the same room. The orange one has helium and the blue one has argon. And after about 12 hours, you see that the helium-filled balloon has very much decreased. It's deflated because the helium was able to effuse out of the sides. It has a higher effusion rate because this helium has a smaller molar mass. So remember, rate of effusion is inversely proportional to 1 over the square root of the molar mass. So as the molar mass is lower, the rate is higher. So this is why the helium effuses faster than the argon. The argon is much more heavy. So with that higher molar mass, it's going to have a lower rate of effusion. So let's look at an example applying Graham's law to rates of effusion. We want to calculate the ratio of the rate of effusion of hydrogen to the rate of effusion of oxygen. So we know the ratio is equal to the square root of B over the square root of A. So since we have hydrogen on top, that means the molar mass of hydrogen gas needs to go on bottom. And oxygen's on bottom, so its molar mass needs to go on top. So this is equal to the square root of 32 divided by the square root of 2, which is the square root of 16 over 1, which is 4 over 1. So hydrogen is going to effuse 4 times as fast as oxygen. Notice we're not looking at the actual rates. We're just looking at a ratio. Okay, so hydrogen goes 4 times faster than oxygen because it's that much lighter than the oxygen. And also notice these molar masses. Oxygen, remember, is O2. Hydrogen is H2. So don't forget that part as well. If you're on an exam, you remember what each gas, what the formula is if you get something like a diatomic. Okay, this next one is actually looking at effusion rates and times. We're told it takes 243 seconds for 4.46 times 10 to the negative 5th moles of xenon to effuse through a tiny hole. Under the same conditions, how long will it take 4.46 times 10 to the negative fifth moles of neon to effuse? So we know we have what the rate of effusion is equal to the amount per time. And we also have Graham's law. So we need to combine these two and put amount per time for xenon divided by the amount per time for neon. So then we get amount of xenon transferred per time divided by amount of neon transferred per time. Now, looking at these amounts, we see that the amount of xenon is equal to the amount of neon. So those cancel out. It doesn't even matter really how many moles of each one we have. All they had to tell us was that the amounts were the same. They cancel out. So then that gets us 1 over the time for xenon divided by 1 over the time for neon. So then that simplifies to the time for neon divided by the time for xenon. And then on the right, we have the square root of the molar mass of neon divided by the square root of molar mass of xenon. And so now we know that the time for neon divided by the time for xenon is equal to the square root of the molar mass of neon divided by the square root of the molar mass of xenon. And so then we can solve for this time for neon now because we know all of these other variables. So then solving, we get 95.3 seconds for neon to effuse. And this makes sense that neon has a shorter amount of time to effuse because it is lighter than xenon. And one more example. An unknown gas effuses 1.66 times more rapidly than CO2. What is the molar mass of the unknown gas? And try to guess its identity. So we're going to use Graham's law. The rate of effusion of our unknown divided by the rate of CO2 is equal to the square root of the molar mass of CO2 divided by the square root of the molar mass of the unknown. We know that the ratio of the unknown to CO2's rate of effusion is 1.66 to 1. Okay, it's 1.66 times as rapid as CO2. So we have our left side. We know the molar mass of CO2. So then solving for the molar mass of our unknown, okay, if we do the square root of the molar mass of unknown, we know that's equal to the square root of the molar mass of CO2 divided by 1.66, and then we have to square everything. So the molar mass of our unknown is equal to the molar mass of CO2 divided by 1.66 squared, and we get 16.0 grams per mole. And if you were to look up, gas with molar mass of 16.0, you would get probably methane. CH4 is the only gas that has this mass. One place that diffusion is used is in nuclear energy. So this is how uranium is enriched. You take some uranium hexafluoride and it goes into this reactor that has a porous barrier. And what happens is the heavier enriched uranium-235 hexafluoride comes out the bottom of the barrier because it diffuses a lot slower, whereas it diffuses faster because it's lighter. The 238 diffuses a lot slower and stays in the tube, so that comes out here, and the enriched 235 uranium is now in this outside part, a lot more of it, and so it comes out the bottom.